Okay, welcome back, everybody. This is our second lecture in GPH 111, Physical Geography. We're going to start big picture. So before we actually dive into what's going on the planet, we're going to take a look at Earth and its relationship to the Sun and how that impacts us. Alright, so we're going to cover where Earth is in relation to the universe. That's about as big a picture you can get. Earth's rotation and revolution, terms important to Earth's orbit, and how Earth's tilt defines much about our climate. Alright, so let's start with some cool facts about the Sun. It's roughly 91 million miles away from the Earth, or at least that's as close as it gets. Sometimes it's as far as 93 million miles away. That's pretty far, which is good because it has a surface temperature of 11,000 degrees Fahrenheit. This is kind of neat to think about. The Sun represents 98% of our solar system. So our solar system includes the Sun and all the planets: Jupiter, Saturn, Uranus, Neptune, Earth, Mars, Mercury, Venus, and the Sun. But if you add those all together, the Sun represents 98%. So another way of looking at it is our solar system is the Sun with some small debris orbiting around it, which is kind of neat to think about. As a result, it's big, and it can hold roughly 1.3 million Earths. And remember, the Sun is generating energy because it is fusing hydrogen atoms, the smallest atoms that we got, which are just protons, neutrons, and electrons, or one electron, together to make helium, which is 2 protons, 2 neutrons, and 2 electrons, roughly. So here's the rest of the junk that's spinning around the Sun. You got, in the inner planets, you got Mercury, Venus, Earth, and Mars. And then outside you have the gaseous planets, Jupiter, Saturn, Uranus, and Neptune. What's neat about that is, let's see if I can do this. Up here, if you see my little red dot, these are the inner planets. They're known as the terrestrial planets. So you could send a lander to land on Mars. You can send a lander to land on Venus and Mercury. Out here in the far gaseous planets, you can't. You can't land on Saturn. You can't land on Uranus, Neptune, or Jupiter. They're the gaseous planets. What's neat is these inner planets used to have a lot of gas associated with them, but during the Sun's development at one point, once it initially ignites, there's a massive explosion and it blew a lot of the atmosphere that was on the inner planets, which was just blown out into space. And that's just one of the tiny facts related to our very dramatic early beginnings of the solar system. Here's pictures of them. By the way, you need to know the names of the planets in this class. You'll be asked them. This is Mercury. It's more or less kind of like the moon. Doesn't have an atmosphere. It's really hot because it's close to the sun. This is Venus. It's farther from the sun, but it's even hotter because there's a massive greenhouse effect going on. It's hot enough to melt lead on the surface. It's raining sulfuric acid, and it's lightning all the time. Unpleasant. Here's our wonderful planet. We'll learn more about that later. Mars, it's farther away. It's cold. And based on all our research, there doesn't appear to be any life on it. It's relatively small, but it has some amazing things. It has the biggest volcano in the solar system, the biggest canyon in the solar system, and it also, recently, there's suggestion that it has plate tectonics, which is neat because only Earth has plate tectonics. Then we got Jupiter, giant gas giant. It has this giant storm on it that can hold like 2 Earths in it. That's been going for a long period of time. Another neat idea is because of reactions in the atmosphere, carbon is generated. And this is totally speculative, but the thought is that carbon rains down into the atmosphere into the core of Jupiter, and under enough heat and pressure, carbon will turn into diamonds. So Jupiter might have a diamond core. Saturn, beautiful rings. Neat fact about Saturn is it's so light it would float on our ocean. Admittedly, there's a scale issue because Saturn's huge, but it has a density less than 1. This is Uranus. It has, some people mispronounce it, but it is named Uranus. Then we have Neptune, and Neptune is our farthest planet out. It's obviously cold. If you were orbiting Neptune, our sun would look like just a bright star in the sky because the sun will be so far away. And lastly, Pluto, which got the boot, isn't officially a planet because it's just it's basically, it used to be a moon of Neptune, and it got hit and now orbits the sun. Okay, but the question at the top, the rest of the solar, oh wait, no, the question isn't at the top. But the question is, where is our solar system? Well, it turns out our solar system is in the Milky Way galaxy. And so here's a rendering of the Milky Way galaxy. Now, we are in the Milky Way galaxy. When you go out at night, on a clear night, and you look up, you'll see a band of stars where they're more tightly clustered together. That's the Milky Way galaxy. But you're in it, so you can't. We can't get a picture of the Milky Way galaxy because we're inside. So this picture that we're looking at is a rendering from a bunch of different pictures taken over several nights to kind of give us a view of the Milky Way galaxy, but it's our view from within it, and we are on the outer edge, which is nice. It's nice to be in the suburbs in a galaxy, because if you're in the city or the inner city, there's a massive black hole. There's supernovas exploding all the time. It's not very safe. And cool fact, our sun is one of 100 billion stars just in our galaxy alone. And real quick, 100 billion, that's an estimate. You can't actually count 100 billion, at least not like 1, 2, 3, 4. I think if you did count that way, you would be 32 years old by the time you ever got to the first billion. So it's an estimate. Some people have it as high as 500 billion, some has as low as 50 billion, but we're going to stick with 100 billion stars. Okay, but where's the Milky Way galaxy? Well, it turns out our Milky Way galaxy hangs out with something called the local group, which is a group of 22 galaxies, and we're all kind of hanging out together. And it's maybe not, I don't know. It just used to be back in the early science days, everything us had to be the best. So Earth was the center of the universe. The sun was the center of the universe. The sun was the center of the Milky Way galaxy. Well, none of that stuff's true. And now we hang out with other galaxies, and we're not even the biggest galaxy. We're the second biggest galaxy, behind Andromeda, which is the biggest. Andromeda's neat. You can actually see it just with binoculars. It hangs out near the W constellation, which is near the North Star. Oh, if I knew if I was talking about this, I would have remembered what the name is. Anyway, it's neat. You should totally check it out one night. It's mind-blowing to think, because all the stars you see in the night sky are just stars in our galaxy, but to actually look out at another galaxy, because galaxies, these other galaxies, they also have 100 billion stars in them. Right? So, dang, that's a lot of other stars. Alright, so but where's this local group? Well, it turns out the local group is in the process of merging with the Virgo cluster of galaxies. What's a cluster of galaxies? So the way you want to visualize a cluster of galaxies is basically like, imagine a ball, and on the outside of the ball are spread 1,000 galaxies. Okay? But on the inside of the ball, there's hardly any galaxies at all. So there's structure. It's basically a bubble of galaxies. That's the Virgo cluster of galaxies. And the local group's in the process of merging with the Virgo cluster, but it's not there yet. And remember, these 1,000 galaxies in the Virgo cluster each has roughly 100 billion stars in it. And then it begs the question, where's the Virgo cluster? Some of these names aren't very creative. It turns out the Virgo cluster is in the process of merging with the Virgo supercluster of galaxies. You think they could have come up with a new name, kind of like the local group. Like, what kind of a dumb name is that? But anyway, a supercluster. So this is a little bit more difficult to think about, but the idea is, so think about that ball again of galaxies, or bubble of galaxies. Now think about a bubble made up of the smaller bubbles of galaxies. So a supercluster of galaxies has clusters all along the outside in a giant bubble, with hardly any clusters of galaxies on the inside, which is mind-blowing. These are the biggest structures in the universe, and a supercluster has over 100,000 galaxies in them. Boom! So my whole point in doing this is, let's get back closer to home. So we're not dealing with astronomy. We're not dealing with all this stuff that's like wicked far away. Take a look at this picture. You're looking at Saturn, taken by a satellite. And what's neat, I mean, this is a real picture. This is not photoshopped. I mean, they process it, but it's not photoshopped. The sun is directly behind Saturn, and this is what Saturn looks like from behind, which is absolutely beautiful. But what's neat is this little dot right there, that's you. That's Earth. That's home. Everybody you know that ever lived, anything you ever knew about, is all right there on that little tiny dot. But anyway, whole point is, let's get back closer to home. Earth. It's not that big, and it's well within your realm of understanding. The circumference of Earth, if you were to drive all the way around Earth, it's only about 24,000 miles. And we all would love a car with only 24,000 miles on it. That's just not that far. We have all driven that distance in our life easily. A lot of us have driven that distance many, many times over. So this planet is well within your realm of understanding. It's not that big. And we're going to learn a lot about it in this class. And it's not anywhere near as big as the sun. But the sun plays a huge impact on Earth, and we're going to look deeper into that. Okay, so what I want you to do now is, I have 2 links at the bottom of this page, and they're also on the Canvas page where you found this video. Go look at those links, and what I want you to do is take a look at how Earth revolves around the sun. A revolution is 1 time around the sun, and for Earth that takes 365 1/4 days. Okay, 1 rotation is 1 spin, right, which takes 24 hours. And what you're going to notice when you watch those videos is the key thing is that Earth, when it spins around the sun, it does it tilted. It's tilted 23.5 degrees. And because it's tilted, that accounts for seasons on our planet. The solar energy is unequally distributed throughout the year. So take a minute and look at those. Okay, cool. Hope you enjoyed those videos. Got a sense for how the sun goes around the Earth. Just a kind of a review. Here's the sun, and we're looking down on the Earth. So here's the axis, and as it spins around in the summer, you can see that the northern hemisphere tilts towards the sun. If you look down here at a side view, you can see the northern hemisphere is tilted towards the sun, so the days are going to be longer. There's a lot more heat impacting the northern hemisphere. This is our summer. Down here in the southern hemisphere, it's tilted away from the sun on June 21st. Therefore, this is their winter. It's very cold and they get very little sun. As you move over here to an equinox, An equinox is neat because there, the sunlight, what they call the circle of illumination, perfectly bisects the planet right there along the tilt, which means wherever you are on the planet, you experience 12 hours of daylight and 12 hours of darkness, which is neat. If you happen to be on the North Pole on an equinox, the sun literally spins around you on the horizon. It never sets and it never rises. Dude. December 21st, our winter, northern hemisphere is tilted away from the sun, and the southern hemisphere is tilted towards the sun, so they're getting really a lot of energy. It's really warm, and up here it's really cold. Swinging back up here to another equinox again, equal daylight and darkness on March 21st. I need you guys to learn all this. I need you to learn that on June 21st, the sunlight, where it's going to hit directly overhead, is the Tropic of Cancer, which is at 23.5 degrees north latitude. Okay? That's because the planet's tilted 23.5 degrees. Up here, you have the Arctic Circle at 66.5 degrees north latitude. Up here, on the summer solstice, they experience 24 hours of daylight north of that line. Down here, they experience 24 hours of darkness south of the Antarctic Circle. Okay, because it's totally in darkness. That's for the summer solstice. You need to know that. On the equinoxes, the sun is directly overhead the equator, and the planet experiences equal daylight and darkness all over the planet on an equinox. On December 21st, on this solstice, the sun is directly overhead the Tropic of Capricorn, 23.5 degrees south. 24 hours of daylight south of the Antarctic Circle, 66.5 degrees. And 24 hours of darkness north of the Arctic Circle, 66.5 degrees north. Okay? All this information about how the Earth travels around the sun, the dates of the two solstices, the dates of the two equinoxes, I need you guys to learn that. And here's what's also kind of neat. Because our planet is a sphere and it spins around the sun, if you're at the equator, the sunlight comes in more or less directly on. Now it shifts a little bit because of that 23.5 degrees tilt, but it's almost always directly on the equator. And so that direct sunlight comes in and it's very concentrated. But as you move towards the poles, you have the same amount of light coming in, but it gets spread over a longer distance. So the energy gets more diffuse. Here, the same amount of energy is coming in, but it gets spread over a larger area of the planet, and it gets more diffuse. So on the whole, this is why you're warmer at the equator and colder at the poles. Here's a cool picture. You are looking at the midnight sun. So this is at midnight. Here's the sun coming down to set, but it never actually sets, and it takes off rising again. If you're going to experience this, it needs to be in the summertime, either in the northern or southern hemisphere, and you need to be north of 66.5 degrees north latitude or south of 66.5 degrees south latitude in order to see this, or in order to experience 24 hours of daylight, which we don't normally experience. Well, we never experience down here in Phoenix. Okay, this diagram, I want you guys to do this. I have a link to this diagram on Canvas under this lecture. I want you to print off that diagram, and I want you to be able to diagram it. I want you to be able to do these things. Label important latitudes by name and degree. Here are the important latitudes: the Arctic Circle, Tropic of Cancer, and Equator, Tropic of Capricorn. I want you to label the solstices and equinox and include the dates. This is the summer solstice, June 21st. This is the winter solstice, December 21st. This is, I gotta make sure I do this right, summer to fall to winter. This is the fall equinox. This is the spring equinox. Label which latitude the sun is directly overhead. The sun is directly overhead the Tropic of Cancer on the summer solstice, the equator on the equinox, which always makes this easy. The equator is where the sun is directly overhead on the equinoxes, and the entire planet experiences equal daylight and darkness. That was kind of embarrassing. Hopefully that helped. The sun is directly overhead the Tropic of Capricorn on the winter solstice. Label where on the planet that is experiencing 24 hours of daylight and darkness. This is 24 hours of daylight north of the Arctic Circle, summer solstice, 24 hours of darkness. South of the Antarctic Circle, opposite over here, 24 hours of darkness north of the Arctic Circle, 24 hours of daylight south of the Antarctic Circle. Excuse me. Okay. Labor on the planet. Oh, and then equal daylight and darkness. That's just the equinoxes. So practice on this diagram. Here's key. Here's the answer. This is it all written out for you, how you should be practicing it. Because you're going to have a lot of questions on the test about this stuff. If you can diagram this thing, you'll be able to get those questions right. No problemo. Okay, so we learned about facts about the sun. I need you guys to know the names and number of planets in the solar system. Remember, Pluto's not a planet. It got the boot. Some people are really upset about that. Number of stars in the Milky Way galaxy, number of galaxies in the local group. I need you to be able to diagram and label Earth-Sun relations to answer several questions on that. Where does our planet receive the most energy? The planet receives the most energy at the equator, receives the least energy at the poles. And I say there at the top of the atmosphere. That's key because later on we're going to learn that it's when you get down to the surface of the Earth, that's not the case anymore. But thanks for listening, and have a good day.